Imagine a battle of wits between a clever forger and a vigilant detective. The forger is trying to create counterfeit paintings so convincing that the detective can't tell they're fake. The detective, meanwhile, is getting better and better at spotting fakes. Over time, both become masters at their craft, until one day, even the forgeries are indistinguishable from the real thing. That's the essence of a generative adversarial network, or GAN. A GAN is not one AI model, but two working in a kind of creative rivalry. The first is the generator. Its job is to create data that looks real. This could be a photo of a human face, a piece of music, or even a handwritten signature. The second is the discriminator. Its role is to judge whether something is genuine or a clever fake. The generator keeps producing data from scratch, trying to fool the discriminator. The discriminator keeps trying to spot the fake. As they train, both get smarter, and the fake outputs become stunningly realistic. Think of the generator as an artist starting with random paint splashes and gradually learning what a real face or document looks like, based only on whether it fooled the critic, the discriminator. It's a learning loop. The generator isn't told what a face is, it learns by failing. The discriminator, meanwhile, is also improving. The better it gets at catching forgeries, the more pressure it puts on the generator to improve its technique. This kind of adversarial training has revolutionized the field of generative AI. GANs can create photos of people who don't exist, transform sketches into full-color images, generate new artworks, or even compose music. They're behind some of the most impressive deepfake technology today, capable of fabricating voices and videos with eerie realism. But beyond creativity and entertainment, GANs have serious applications in business and industry. For example, in the insurance world, companies often need to test fraud detection systems. However, there may not be enough real examples of fake claims to train the system well. That's where GANs come in. An insurer can use a GAN to create thousands of synthetic images of doctored car photos or forged documents, giving their detection models a rich training ground to learn from. Still, GANs come with challenges. They are famously difficult to train. The balance between the generator and discriminator is delicate. If the generator gets too good too quickly, or the discriminator too weak, training breaks down. Sometimes, the generator might fall into what's called mode collapse, producing the same kind of output over and over again instead of a variety. They also require careful design and tuning. Over the years, researchers have built improved versions. DCGANs work especially well with image data. Cycle GANs can convert one type of image into another without needing matching examples, for example, turning a photo of a summer street into a snowy version. Style GAN, developed by NVIDIA, is behind the most photorealistic faces ever generated by machines. Others like Pix2Pix and WGAN bring even more stability and versatility. To sum it up, GANs represent a brilliant idea: use competition to drive creation. By pitting two neural networks against each other, one trying to create, the other trying to detect, you get an engine capable of producing realistic, high-quality data. Whether it's helping fight fraud, generating synthetic datasets for training, or creating entirely new forms of art, GANs have opened up a whole new world of machine-made imagination.